Okay, we're going to continue focus 12. We're going to finish it up. So we're on section C where we're um, understanding how you can get thermodynamic properties from the partition function. So let me turn on the camera. Okay, so at the end of my last lecture, we were working on a problem on calculating entropy. And I had to stop because I didn't agree with the equation they were using. So I'm going to explain to you. So this is self-test 12C.3 on page 1515. And it says the rotational partition function of an ethene molecule is 661 at 25 degrees. What's the rotational contribution to its molar entropy? And so the question really was, do we use equation 4b or 4c? 4c is an equation for gases, and ethene would be a gas. So indistinguishable particles. And the important thing about the difference in those two equations is this, that if you have distinguishable particles, so like particles locked in a solid structure where you can identify each particle's location, then the partition function of the system, capital Q, which your textbook doesn't even cover, but you'll see that if you take more statistical mechanics, is just the Q for each molecule raised to the number of molecules. So it's the partition function of each molecule multiplied out, and that makes sense. So, but if you have indistinguishable particles, particles that can move around, then it's a partition function raised to the n for an individual molecule. But you have to correct for the fact that a molecule could be in the upper right-hand corner or the lower right-hand corner, and you can't distinguish which molecule that is. So you don't have quite as many states, so Q is smaller if you can't distinguish the particles, and you can't say energy in the molecule up here is different than energy in the molecule in another location. And so the Q for the system would be Q rotational, Q vibrational, so these are molecular partition functions, Q electronic, and then the translational partition function is usually the one that's divided by n. So Q to the n, so for each mode raised to the n, product of each, and then the whole thing's divided by n factorial. And that n factorial is correcting for the fact that you can't distinguish particles, so you don't have as many states really as you would if you could tell the particles apart. But it's usually the translational partition function that's divided by n, because that's the what you can't distinguish. You can't distinguish whether this molecule is in this location or it's moved to a different location. So when you're talking about just QR, just the rotational contribution, you can use equation 4b, yes, the one where they leave out the n. So we're going to use equation 4b, and we're going to plug in. So, and then it turns out I still don't get their answer because I think they're wrong. Ethene is a non-linear rotor, so it has three different modes of rotation. So 1/2 RT for each rotation, which means you get 3/2 RT is the internal energy relative to 0. When you put that in here and divide that by T, then you're going to put Na times K because you want the contribution to the molar. So the number of molecules will be Avogadro's number times Boltzmann's constant gives you R. And then it'll just be natural log of Q rotational. And I get 7.99 R is the entropy contribution from rotation. So you would use equation 4b, not 4c, because that n comes in when you're talking about the translational partition function. So, okay. I can't remember where I put the other sheets, but now we're going to move on to kind of the grand finale of hooking things together, and that's to an understanding of the Gibbs free energy, because we know that it's the Gibbs free energy that tells us about equilibrium. So the equation that we're going to derive is equation 5 that says what the Gibbs free energy is as a function of the partition function. And then we can go from there to knowing how that relates to an equilibrium constant. So let's do that. I don't think we need these papers. We need it to be bigger to actually follow the derivation. So our definition of the Gibbs energy is H minus Ts, and H is U plus PV. And if we're talking about gases, so what we're going to derive is an equilibrium constant only for gas phase reactions. And if we assume that the gases are perfect, then the PV term is equal to nRT, and nR is equal to the number of molecules times K. So you could write that either way. And so G would be H, which is U plus PV minus TS. So H is U plus PV, then minus TS. And so it's U minus TS plus NKT, because we're replacing the PV with NKT. So we're just taking this into account. Then we're going to remember that earlier, and you could look at it here too, if you look at this equation right here, if you're at absolute zero, then this term is zero and this term is zero, and therefore the Gibbs free energy at absolute zero is equal to the internal energy at absolute zero. So if you make that substitution, plug it in, and so what you're plugging in is you're just subtracting G0 from this side and U0 from this side, but if they're equal to each other, you're subtracting the same number from each side. And then we can just group the terms. So now entropy from the equation that we looked at in the last lecture is U minus U0 over T plus NK ln of Q minus NK ln of N minus 1. And so this is for gas particles. So only for gas phase reactions. And now we can even simplify it more. So if we look at this and I plug in our definition of entropy, so I go back to this equation. So G minus G0 is equal to U minus U0 minus T times all of this. So this is our entropy, U minus U0 over T plus NK ln of Q minus NK ln of N minus 1. And then after we put that entropy in, we still have plus NKT. And so we will just look at how you can group these. So now the T over T cancels, and this term will subtract this term. So all we'll have left are those terms, and we're going to group them together. And when we group them together, we get, because you have a T here, so we're going to multiply through by T and group them together. So you'll get T NK times 1. So when that's a negative, that's where this term comes from. This term comes from right here. And then these two terms, are just this term times T with a negative sign. And then this term with the NKT ln of N. So once we simplify all of that, this term cancels this term, and then you just have to group these two together. And so if you pull negative KT out front, then negative NKT would just be ln of, or would be negative ln of N. And didn't write that here, but you should remember that ln of X minus ln of Y equals ln of X over Y. So if we have negative RT ln of Q, and if we're now changing this to negative, that means we're subtracting NKT ln of N. And so that means that because this is negative, then the n's going to go on the bottom. And so G minus G0, or G at absolute zero, is negative NKT ln of Q over N for perfect gas particles. So we had that in our derivation. So we're going to use that equation, and this will be something you want to pay close attention to, and you can go back and listen to it. So we remember from Gen Chem and from our thermodynamics chapter that delta G for a reaction under standard state conditions is equal to negative RT ln of the equilibrium constant. So now that we know how G relates to Q right here, then we can plug this in for G and solve for K in terms of the partition function. So when we look at a reaction, if we want delta G standard state for the reaction, it would be B. So if this was our general expression, both gas molecules go to B of B gas molecules. So we take products minus reactants. And if we're talking about the molar Gibbs free energy, we'd multiply by the stoichiometric coefficients. And if it's molar, then everywhere where we saw N, it's going to be Avogadro's number. And it's standard state, so the pressure we have to choose is P standard state of 1 bar. So let's go through this carefully. So if we look at the product, the molar Gibbs free energy standard state for B would be equal to what we had right here. It would be equal to, so we just took this over to this side. So the Gibbs free energy standard state, if we take the 0 point Gibbs free energy to this side, will be the molar standard state Gibbs free energy at absolute zero minus NKT, which is equal to RT. ln of the partition function is the molar partition function standard state for B divided by Avogadro's number, because we said we're talking about a mole. So we're going to do that for both A and B. And if we need to know the delta G for the reaction, then we have to take the molar quantities and multiply them by their stoichiometric coefficients. So we're going to take what we just wrote out for B right here, multiply it by the stoichiometric coefficient, subtract from that A, the stoichiometric coefficient, times the standard Gibbs free energy for the A. Then, I don't think we need that anymore. We're going to remember that the standard state molar Gibbs free energy at absolute zero is equal to the internal energy molar standard state at absolute zero. So everywhere that we see the Gibbs free energy at absolute zero, we can put in the internal energy at absolute zero. And so if we take the difference, this is the difference in the Gibbs free energy if we were at absolute zero. It's equal to the difference in the internal energy if we're at absolute zero. And your book just simplifies that and calls it delta E. Most books would call it delta E for the reaction under standard state conditions. And they would put a zero here because it's the difference in the energy at absolute zero. Your book just does that, which is to make it look simpler, but it's not quite as precise. So now we want to go from here into how this relates back to the equilibrium constant. So where we saw the difference in the 0 point energies, so this term minus this term is now delta E. And then we have the negative RTLN, the partition function of B over NA raised to the stoichiometric coefficient. And the way that works out is that if you have B times ART ln of something, it's true that X times ln of Y equals ln of Y to the X. So we can put the B up here. And then we have negative and negative. Yes, two negatives, which make this guy positive. And so we get the same situation where we had A out front, the stoichiometric coefficient, but it will go into the exponent because of the laws. Okay, so we're getting closer. So now we want to combine all of this stuff. So if we have negative RT times each of these, yeah, because then the negative multiplies through, and that should be positive. I feel like the ln of B, no, that's true. If we keep the negative here, then this is ln of x minus ln of y, which is ln of x over y. So that puts the partition function for A down in the denominator, as long as you keep the negative RT out front. So if we group those together, and then this term just comes from, you're always having Na in the denominator for products and reactants. And so that ends up being however many NAs you'll have is Na raised to the A minus B. So if you had equal stoichiometry, if A and B were equal to each other, if you just had 1 mole of A going to 1 mole of B, then all the NAs would cancel. But this term just takes into account how many don't cancel. So here we have our relationship in terms of partition functions. Now we want to actually get it from a delta G into a K. So I am going to divide delta G naught by negative RT. And then this should still have an ln on it. And then, yeah, then I'm going to put it in, just a second. So divided by RT. Okay, so now I'm just putting in what I had up here. So I'm dividing this whole thing by negative RT. So if you divide delta E by negative RT plus this guy divided by negative RT, just gets rid of the negative RT and you just have the ln term. And then if we want to get the, so this is also equal to ln of K. If we want to get the K out of the natural log, then we're going to take E and raise it to both sides. So e to the negative delta G standard state divided by negative RT is equal to K, which is equal to E to the this guy, which is negative delta E over RT, plus all of this stuff. So we're just raising E to both sides. And if you remember, E to the A plus B equals E to the A times E to the B. So that will allow me to split up these two terms. So it will end up being E to this times E to this. And when you do that, this term just becomes E to the minus delta E over RT. And this term, when you take E to the ln cancels, and you're just left with that Q ratio. So you can completely calculate an equilibrium constant from partition functions. And you can completely calculate a partition function either from spectroscopic data, things like the fundamental frequency for the vibrational partition function, the rotational constant, electronic state energies. You can either do that from experiment or you could do it in calculations. You could use a software package to calculate those molecular properties. So when we come to class, we will actually use this equation together and we will try to calculate an equilibrium constant from calculated properties of molecules, and we'll do that as a group so that you see exactly how you can use that equation. And so I think that is it for statistical mechanics, statistical thermodynamics. And we have one chapter left, which is kinetics.